So, hello everyone. I am Anuj Kumar, Prime Minister Research Fellow and TA for this course, Coordination Chemistry. Okay, so today I will be taking the revision session for this course. Okay, so basically, what I have done in this revision session, I have jumbled all the questions of previous sessions. Okay, and one by one I will be discussing the logic behind solving that those questions and yeah, so by seeing this session you can just revise your previous classes. Okay, so I am now starting the session. Okay, yeah, so as usual I will be showing two problems, and I will be discussing the answer of those questions, right? So yeah, so there is a course plan. You are already familiar with that. In week one, we have discussed the introduction part, that is definitions, classification of ligands, ligands like monodentate, bidentate, tridentate, and tetradentate, and so on. And in week second, we have discussed the nomenclature. And in week three, we have talked about the coordination number and their stereochemistry. And week four, uh, the structures of the coordination compounds, different geometries like octahedral, tetrahedral, and uh, trigonal, prismatic, pentagonal, bipyramidal, like that. And some concepts about coordination equilibria, that is stability, formation constants. Okay, and in week 5 we have discussed some bonding theories like valence bond theory, crystal field theory, right? And later on we have discussed the ligand field theory. Okay, so this to explain some phenomena. And in week 6 we have discussed the Taylor effect and spin crossover, right? And okay, so here what is the basic summary for this course, right? So first we have to uh, read the introduction, right? Their structures, their magnetic properties, right? And their colors, and finally the transitions responsible for these colors. Okay, and for transitions particularly you will be reading orgel diagram and Tanabe-Sugano diagrams. Okay, and thereafter application of crystal field theory and some spinels diagrams, right? And magnetochemistry and ligand field theory, and at last you will be reading about the reactions, that is uh, given by the coordination compounds, octahedral complex, and square planar, and rest of others. The activities and some biological inorganic chemistry structures, like because they contains metal, and metal is very responsible for the activity of these biological structures. Like in hemoglobin and myoglobins you have different amino acids. Okay, and in oxygen transfers hemoglobin is involved, right? And thereafter yeah, okay, so I will be discussing the problems starting from week 1 to week 11, because in last Saturday you have discussed we have discussed already about week 12 content, that is basically related to the reactions part and biological part. Okay, so yeah, first question is related to Werner theory. There are some primary and secondary valencies. Okay, so primary valencies are basically ionizable and they can easily form the precipitates. So in the first question, it was asked that how many moles of silver chloride, right, are precipitated when excess amount of silver nitrate is treated with 1 mole of this, right? So here you can see there are three chloride molecules that can be react with the silver nitrate and precipitate in the form of AgCl. So the 3 moles, okay, 3 moles of silver chloride will be precipitated out, right? Okay. The second one is about the ligand denticity, the number of donor atoms present in mono dentate ligand. Okay, in monodentate ligand you have a one donor atom, and similarly for bidentate you have two, and so on, right? So like in EDTA you have denticity of 6, okay, because you have 6 donor atoms. So on, as it is written here, monodentate, so you can, yeah, choose the answer 1. Okay, clear? Okay, so moving to the next slide. So which one is not an example of monodentate ligand? Okay, right. So in NS3 there is only nitrogen which can donate its lone pair to metal center. In water it is oxygen, right? In thiocyanato N, because nitrogen is specified here, okay, so it will be present in the form of NCS. Only this atom will donate the electron to the metal center, so that's why it is also an example of monodentate ligand. Although if it was, if it not specified, that is if it is only thiocyanate, so it can exist in two form, it isothiocyanate or thiocyanate, it can be NCS or SCN. Okay, in that scenario it can work as a ambidentate ligand. Okay, and oxalato, since oxalato is this structure, okay, so it is bidentate. Okay, so this will be the right answer because it is not an example of monodentate ligands, right? So next one, which metal ion is responsible for the blood red coloration with the addition of this ligand? So in the blood it is metal plus 3, that is iron plus 3, sorry, that is making complex with this ligand and responsible for the blood red color, right? You can just read about the uh, charge transfer transitions, okay, which one is taking place in this case. Okay, so how many non-bonding orbital is available in ammonia molecule? Okay, so since here this ammonia is 3 electrons are connected through single bond with hydrogen, and one is remaining here. Okay, so this lone pair is non-bonding, that is easily available for donation to metal. So one non-bonding orbital. Okay, among the following, which ligand can act as a ambidentate ligand? So as I have already told you, that ambidentate ligand is that uh, which contain which contain more than one donor atom. Okay, so it can join through any of them, right? So for that purpose, both the atoms should have lone pairs. Okay, so in this case only phosphorus is there, so there will be no denticity here. Okay, in case of phosphorus, oxygen can donate its lone pair, but phosphorus does not contain any lone pair because its 5 electrons is present in its outer orbital and 5 are already involved in the bondings. In case of this, you have lone pair with sulfur and oxygen also, so it can work as a ambidentate ligand. Okay, right. So what is the reason and formula of the blood red complex formed with iron metal ion? Okay, so what is the formula for the complex that is formed, and what is the reason, that is metal to ligand charge transfer or ligand to metal charge transfer? Okay, yeah. Just see these two problems and try to solve, because you have already solved these problems in your earlier assignments. Okay, so in this case, because there is blood red coloration, so metal to ligand, ligand to metal charge transfer is taking place, and this complex is formed. Okay, and which of the following complex have tetrahedral geometry, right? So just write down their electronic configurations and fill uh, in their respective d orbitals. You will be getting the hybridization. Okay, and according to that hybridization you can determine the shape. Okay, this concept have extensively discussed in the classes. Okay, so first write down the oxidation state. That is, if I consider this example, it will be cobalt +2. Okay, so it will be 3d7. Okay, and in this case, because and this is platinum. Okay, and this is the element of 5D series. So since 5D series have form the square planar complexes mostly, right? And consider this one, that is 3D uh, nickel +2. It will be 3D8. Okay, right? And according to the behavior of this ligand, you can just pair up the electrons, right, and determine the hybridization. Okay, right? Yeah. So which will be the right answer for this question? Yes, one. Okay. So next one is, what is the coordination number and oxidation state of cobalt metal in this complex? Okay. So it is very simple. The coordination number is 2 plus 2 plus 2 is 6. Okay. And what is the oxidation state? Okay. So since it is a neutral molecule, it is also a neutral molecule, but chloride is -1. Okay. So it will be +3, right? And what is the oxidation state of chromium in this complex? Let's consider it x minus 2 into 1 equal to +1. That is +3. Okay. So arrange the following: the compound that is both paramagnetic and colored. Okay, so just write down the oxidation state, because here Cr2O7 minus 2, and here LiCl6 minus 2. Okay, and here vanadium plus 3, sorry, plus 4, and the CuCN4 minus 3. Okay, so what is the coordination, sorry, oxidation state of lithium here? It will be X minus 6, it is plus 4, and vanadium is already plus 4. And what about cobalt, sorry, copper? It is minus 4, minus, it is plus 1. Okay, so it will be D9. And what about this one? Sorry, it is 2x minus 14 equal to minus 2, x equal to plus 6. Okay, right? So in this way, you can just, okay, write down the electronic configuration in the orbitals. Fill the orbitals with the electrons. Okay, so vanadium plus 4, it is uh, D1, right? So here it is paramagnetic, because there is no pairing of electrons. And colored, because this is paramagnetic, it can transit up to the higher state and can show the color, right? Just try the other one also. Okay, whenever I will share the PDF, I will give you the right answer, because it is just for your practice. Okay, yeah. Moving to the next one, that is calculate the oxidation state of metal ion and number of unpaired d electron present in the complex this. Okay, so here is also d8, right? And the oxidation state will be plus 2. And what will be the unpaired electron? Because the cyanide ligand, cyanoligand is a strong ligand, it will pair up all the electrons. Okay, and yes. Okay, so point out the correct statement of the following: this complex has tetrahedral geometry and dsp2 hybridization. Okay, or this complex is octahedral, and basically you have to determine the hybridization and their magnetic nature. Which one of the following complex have tetrahedral geometry? Okay, I think this question have been repeated. Okay, just try to solve the first one. I'm waiting for 2 minutes. Okay, so in this case, zinc in plus 2 oxidation state, right? And since it is a weak filled ligand, so it will be forming tetrahedral complex. Okay, and if I write the electronic configuration for zinc plus 2, okay, it will be 3d10. Okay, and means if it is, yeah, dimagnetic, because all electrons are paired up. Okay, so what is cyclum? It is classified as a crown ether, yes, because crown ether has oxygen. Since it is having nitrogen, it is as a crown ether. Its IUPAC name is 14811 tetra cyclo tetra decane. Okay, just count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, right? So you can see here at first 4, 8 and 11 position is having nitrogen. So 1, 4, 8, 11 tetraedra cyclotetradecane is also right IUPAC name. It binds the metal ion through 4 nitrogen atoms. Yeah, it can bind here through these 4 nitrogen atoms. Okay, and which one is correct statement for box ligand, right? So bis oxazolene ligands. Okay, so it is an achiral organic inorganic molecule. Box is the bis oxazolene contains 3 oxazolene units. No, it is containing 2. Okay, the coordinated complex of this ligand is useful of asymmetric catalysis. Okay, it is an achiral or inorganic molecule. Basically, it is a chiral molecule. Okay, so the coordinated complex is very useful for asymmetric catalysis. Okay, so the IUPAC nomenclature of this, because first you have to write down the name for cation, that is plus 1 6. Okay, and since it is an anion, you just add just see which suffix or prefix will be added here. It will be phosphate, phosphine, or phosphite. Okay, and both the problems are based on the nomenclature. Just try. Okay, so since it is phosphorus is in anion form, so that will be uh, 8 will be added, right? So what will be the name? So oxidation state is 5, so sodium hexachlorophosphate. Okay, and in the second one you can see there are 2 bitentate ligand. So in this case you just add bis, and write down the name of that ligand. So there is one options only in which it is written the chlorobis ethylene diamine nitrite of cobalt. Cobalt it is in plus 3 oxidation state. Okay, because minus 1 minus 1. Okay, yeah. So which geometry does not belong to the coordination number 6? Okay, yeah. So since in a square planar you have 4 coordination number, in octahedral you have 6, right? In hexagonal planar you have also 6, and in trigonal prism you have also 6 because it is structured like this. Okay, so square planar will be the right answer because it does not belong to the coordination number 6. Okay, and what will be the geometry of BF3 boron trifluoride? Because it is trigonal planar, but when the fluoride is added it just become the tetrahedral molecule. Okay, so here is the explanations. When the central atom or ion is attached to 6 atoms or ligands, then the coordination number will be 6. For coordination number 6 there are 3 different types of geometry is present. Okay, you can see here there is a trigonal prismatic structures and octahedral and hexagonal planar. You can observe that for all three shapes and geometries the coordination number is 6, but for square planar geometry 4 ligands are attached, so that's why the coordination number is 4. Okay, and in this case you can see first it is trigonal planar and later on it becomes the boron trifluoride, sorry, tetrafluoride anion that is tetrahedral in nature because the hybridization is changed from sp2 to sp3. Okay, so first one is trigonal planar and second one is tetrahedral. Okay, so which one of the given below is known as Vasquez complex? Okay, in Vasquez complex metal, which metal is present? That is iridium. Okay, so if I see the structure here, you can see one chloride is here and one carbonyl, right? And rest is the pph3 molecule twice. Okay, so you can see one phosphorus is connected to through, sorry, 3 phenyl rings. Okay, so this is called Vasquez complex. Okay, and central metal atom is present in plus 1 oxidation state. Okay, so which will be the right answer for this one? That is trans chloro, because here you can see the positions of chloride and carbonyl, that is trans. Okay, so trans chlorocarbonyl bis triphenyl phosphine iridium in plus 1 oxidation state because there is one chloride. Okay, and which molecule can show Berry pseudo rotation? Basically it is observed in trigonal bipyramidal complexes. Let's say if it metal, this ligand and these two. Okay, so what is this phenomena? In this pseudo rotation, axial bonds become equatorial and equatorial become axial. Okay, so you can see here only PF5 is trigonal bipyramidal type of molecule, so it will show Berry pseudo rotation. So here same thing is shown here. Okay, so after rotation you can see this red fluorine is has gone to this place, and this green fluorine gone to this place, and similarly for others. Okay, so axial changes to equatorial and equatorial changes to axial. Okay, Yeah. So which one is the trigonal prismatic complex? Okay, so you can see here is these complexes are square planar in nature because four ligands are attached. Okay, but in this one tungsten hexamethyl complex, it is trigonal prismatic complex. Okay, so you can see this one. So the trigonal prismatic molecular geometry describes the shape of compounds where six atoms, group of atoms or ligands are arranged around a central atom, defining the vertices of a trigonal prism. Here, this is the first example of this type of shape. Okay, tungsten as the center and six methyl are connected. Okay, what is the Wilkinson catalyst and what will be its geometry? Okay, so you all know that is Wilkinson catalyst. It widely used in cis hydrogenations of alkene. Okay, and it is having a square planar shape. Okay, just see here. This is chloride and one pph3, other pph3, and third pph3. Okay, so this one. Okay, what are the stereoisomers? So we are moving to the stereochemistry part. And what are the stereoisomers? So isomer with different spatial arrangements. Yeah, see, this one is only a right answer because they will be same. How they can have the same spatial arrangement, because that will be the identical molecule. Okay, the second is which ligand is applicable for exhibiting linkage isomerism. Okay, so basically the linkage isomerism is shown by ambidentate ligands because they have more than one donor atom and they can connect to the metal center through any of them. Okay, so you can see in all these three ligands the metal can join through either sulfur, nitrogen, or oxygen. Okay, so if I discuss about the types of isomerism that is found in coordination compounds. Okay, so one is stereoisomerism, that is basically related to the spatial arrangement. In the stereoisomerism, you talk about geometrical isomerism, cis and trans, optical isomerism, D and L formed exploratory and laboratory with respect to the light phenomena. And in structural isomerism, you can have solvate isomerism or you can say hydration isomerism, that is basically defined by the number of uh, water molecules inside and outside the sphere. Linkage isomerism is related to the connecting atom. Coordination isomerism is related to the coordination number. Okay, the ligand may be ligand is different, but the oxidation number is same. Okay, and metal can also be okay. So you can see here. Okay, so these are the coordination isomers. Ionization isomerism, you can see here outside the coordination of a sphere, it is bromide ion, and in this case, it is sulfate. So if the outer sphere have a different uh, ionization entity, or you can say, because in this first case you can see sulfate is inside the sphere, and in second one it is outside the sphere. So these type of uh, molecules will show different ionizations because it will donate bromide and it will donate sulfate. Okay, so they are called ionization isomers. Okay, so yeah, so what type of isomerism is present between these two complex? Okay, It is geometrical isomerism or coordination sphere, linkage isomerism, or optical isomerism. Okay, so ignore these structures. Okay, and just draw their structures and what information you will be getting, because you can draw the primary and secondary valencies. Okay, so it will be having coordination sphere isomerism. Okay, because here are three chloride, and in this case there are two chlorides. Okay, the types of isomer present in this complex, yeah, they can have cis and trans isomerism. Okay, facial and meridional isomers I have already told you in during the assignment, I think 3 or 4. Okay, it is it is usually happening in Ma3B3 type of complexes. Okay, and delta lambda isomers is uh, found in the complex having metal tris chelates. Okay, so here it is there is no any tris chelate ligands, so cis trans isomers will be the right answer. The second is how many structures possible for this. Okay, so as I have already indicated the solution structures. Okay, so it can exist in four types of structure. Okay, and this is the platin molecule that can exist in cis or trans form. Okay, in this case you can see the chloride are cis and here the chloride are trans, or you can talk about with respect to these ammonia molecules. Okay, so two isomers will be the right answer for this one. Okay, so there is one complex that is reacting with NaNO2 in presence of concentrated HCl to form a compound which exists in both yellow and red form. So what isomerism is expected here? Okay, so basically this coloration is dependent upon the metal ligand bond. Okay, so whether you are having a cobalt nitrogen bond or cobalt oxygen bond. So you can see in this reaction, so here this is the NO2 ligand. Okay, so it can connect through oxygen or it can through connect through the nitrogen. So this type of isomerism is called linkage isomerism. Okay, okay, so these concepts have been already discussed in the respective assignments. Okay, and what about this one? So you can see here Fe plus 2 is in outside the coordination sphere. In this one it is inside, so it is exhibiting coordination sphere isomerism. Okay, so these two questions are related to the stability of complexes, or you can say the stability constant, that is a measure of their stability. Okay, so instability just reverse of stability constant. So here you can see there are two complexes, and for them the values of instability constant are given. Okay, and you can see if I consider is k2, k2 is very less, and if C1 and C2 be the concentration of silver ion in equimolar solution of these two complexes, so C1 and C2 will be related as, because this the stability constant of K2 will be higher, so it will not lose their silver ions. Okay, clear? if the instability constant is higher for K1. Okay, so what does that mean? It is easily dissociating, and it will easily give the silver ion in the solution. Okay, so you can select the answer accordingly. I think this will be the right one. Okay, same here, the addition of potassium iodide solution of because uh, precipitates AgI. Okay, if the complex is stable, why it will lose their ions in the solution and form a precipitate? Okay, so addition of Ki to solution, this precipitates AgI, but no precipitate form when Ki is added to this. Okay, of same color. If the instability complex of K1 and K2 is given, so if it is uh, donating their silver ions in solution, so the instability constant will be higher in this case. Okay, so this will be the right answer. Okay, so you just apply your theoretical concepts and you will be getting the answers. Don't deviate from these values. Okay, just it is for your quantitative analysis that the value which one is lower and which will be higher. Okay, yeah. So what is the geometry of this complex? Okay, since I have discussed many of the questions like this, so just write down the electronic configuration. Okay, so what you have to do, that is nickel in plus 2 oxidation state, it will D8. Okay, let's say 1, 2, 3, 4, 5, 6, 7. Since it is sorry, it is ligands, so it will be pair of these electrons. So electrons configuration will look like this, right? So since it is a 3D orbital, it can combine with uh, 4s and 4p. Okay, so one cyano ligands will donate their electrons here, one is here and two is here. So it will be having a dsp2 hybridization. So what will be the shape of dsp2? That is square planar. Okay, and second is, in the presence of an octahedral field, no splitting occurs for which orbital? Okay, so s and p orbitals are not splitted. Okay, so yeah, here is the explanation. You can see the complex is square planar, and in the second one, in the influence of an octahedral field, the split orbitals split into T2z and EZ. P orbitals are triply degenerate, having T1g symmetry in the point and do not split in the remain and in the energy and remains in T1g energy levels. Okay, so s orbitals become present in A1g and the p orbital do split into this. So s and p, they do not split. Okay, so which one of the given complexes is paramagnetic? Okay, paramagnetic means which one have the number of unpaired electrons. If they all are paired, it will be diamagnetic. Okay, so first check the oxidation state, write down the electronic configuration, fill them according to the, yeah. So since here cyano ligand is a strong ligand, so in all the cases electrons will be paired up. Okay, so in this particular question, the magnetism is only dependent upon the uh, number of unpaired electrons. Okay, so here is also Fe plus 2, copper plus 2, and nickel plus 2. and it is also nickel plus 2. Okay, so it is DsP2 square planar complex. Okay, and in the last slide I have shown all the electrons are paired up, so it will be diamagnetic. And what about this one? Okay, so in this case chloride ligand is given. So in D8, because chloride is a weak ligand, so number of unpaired electrons will be 2 in this case. So that's why it is paramagnetic. Okay, which one is the correct statement for crystal field theory? It is a purely covalent model for transition metal complex. It cannot predict the splitting. CFT is known for the splitting. Ligands are considered as a point charge. Yeah. So because in CFT, the metal ligand interaction is purely ionic in nature, so ligands are considered as a point charge. It cannot explain the color of transition metal. This is also incorrect statement, and this is also incorrect. Okay. Yeah. Okay. So up to here, we just uh, covered up to this bonding in complexes. Okay. Okay. So in this question, what is the geometry of cobalt tetrachloride complex, and how many unpaired electrons present? Okay. So here cobalt in plus 2 oxidation state, it will be 3d7. Okay. So three unpaired electrons will be there. Okay. And what will be the hybridization? Since these chloride ligands cannot donate their electron pair here, it will be accommodated in next orbitals, that is 4s and 4p. So that's why the hybridization will be sp3. Among the complexes, which one is sp3 hybridized and dimagnetic in nature? Okay, so I have discussed this one already. It is square planar, and this one is already discussed here. It is sp3 hybridized but not diamagnetic. Okay, just see this one. It is d10. Okay, so it is independent of whether it is connected through weak ligand or strong ligand, it will be diamagnetic. And also it is a tetrahedral complex. Okay, according to hard soft acid base principle, which is not a property of hard acid, hard base. Okay, so basically hard means they are having very high oxidation state, less size. Okay, so large ionic radius is not a property of hard acid, hard base. Okay, they have low polarizability means the electron cloud uh, cannot be easily distorted. That is called the polarizability. High electronegativity, yes. High oxidation state, because in high oxidation state metal is having very less ionic radius. Okay, amongst the following, the complex ion that is expected to show the highest magnetic moment at room temperature. Okay, so there is no temperature based transitions. Okay, because sometimes the thermal energy, that is room temperature, the kt, can induce the spin crossover. Okay, so you have to just neglect that. Okay, so highest magnetic moment means highest number of unpaired electrons. Okay, so in this case it is nickel plus 2, that is d8. It is Fe plus 3, D5. and it is D9, copper plus 2, and cobalt plus 3, D6. Okay, so in this case, FeCN6. Okay, just fill them according to CFT. So on one unpaired electron. Okay, and in this case, D8. Oh, okay, since it is a square planar molecule. Okay, first just observe for this one, that is D9. Since it is a weak field ligand, it will be 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, so one unpaired electron is there. And what about this one, that is plus 3? It is D6, so they will be paired up in T2Z level. And what about this one? Okay, so highest unpaired electron will be in this one, so that's why the highest magnetic moment will be shown by this complex. Okay. Okay, so just confirm at your end whether it is right answer. Okay. So moving to the next problems. Okay, so just confirm among these two, and while calculating, just keep in mind that which one can contribute to orbital magnetic moment also. Okay, because in this case, the T2Z will be unsymmetric, so it can have a orbital contribution. Okay, so in my thinking, it should be the right answer. Okay, which transition is responsible for the coloration of complex? That is, this is octahedral complex and titanium plus 3. It is D1. Okay, So from orbital diagram, just confirm D1 in octahedral will be lying in which side. Okay, and from there you can just, yeah, T2Z to EG in octahedral complexes. What do you mean by strong field ligand? Where delta no O is greater than P. Ligand causes low crystal field splitting, no. Large splitting, yes. Favors unpairing of electrons, no. It favors pairing of electrons. Okay, so forms high spin, no. Low spin complexes. So this will be the right answer. Okay, so let me go to the orbital diagram. You can check, here is D, this is T2Z, this is EZ, here D1, D6, and D9 and D4. This is octahedral complex, right? So right answer is first one. In Jad-out situation of the octahedral complex, the higher energy state is because the Jad and the bond axis, sub bond along the Z axis is out. That is, it is stabilizing the, it is lowering the energy. So in this case of Jad-out situation, the energy of D orbital with Z factor, dz square, dxz, yz are lower. Okay, and this is most preferred distortion and occurs because the John Taylor distortion. Okay, for overcoming the repulsion between metal electrons and the ligand electrons, the bonds get elongated and compressed in some cases. Okay, and you should be you should have a knowledge about static and dynamic John Taylor distortion also. So in this case, the highest energy state will be dx square minus y square because these terms will be stabilized. Okay, what will be the crystal field stabilization energy of high spin T4 system? So high spin means, and since O is given, that is octahedral complex, you have to consider. So 1, 2, 3, and 4. Okay, it will be plus zero point 0.6 from barycenter, it is minus zero point 0.4 delta naught. Okay, so what will be the energy, that is zero point 0.6 del naught minus uh, 1.2 delta naught, that is zero point 0.6 delta naught, and you can see, you can return, write down minus 3 by 5 delta naught. Pairing energy will be 0 because there is no pairing. Okay, what do you mean by the John Taylor effect? It is type of geometric distortion. Yes, it is correct. It is observed among octahedral complexes. Yes, and it is reduces the symmetry and energy of the non-linear molecular system. All statements are correct. Here is the explanation. You can read down. Okay. The next is, which one of the given systems exhibit strong John Taylor distortion? Low spin D2 system, high spin D9 system. So in case of high spin D9 system, okay, so you can see easy is unsymmetry here. So in this case, you will observe the strong John Taylor distortion. Okay, although in case of unsymmetric t t2z orbitals, they can exhibit the John Taylor distortion, but that is very weak. Okay, so what do you mean by SCO, spin crossover phenomena? Basically, it is a phenomena that occurs in some metal complexes wherein the spin state of complex changes due to an external stimulus. The stimulus can include temperature or pressure. So basically, if the complex here in low spin and some external stimulus is applied, that like temperature or pressure, it can change up to high spin, and this region is called spin crossover region. Okay, so it is a spin equilibrium behavior. The change in the spin state usually involve the interchange of low spin and high spin configurations. Okay, so it is a phenomena where spin is changed by external stimulus. First is yeah. So which techniques can be used to detect the SCO? All these techniques can be used. Magnetic susceptibility measurement using Gauss balance, Mossbeer spectroscopy, Raman spectroscopy. Okay. What is the correct statement for low spin complexes? So you know del naught is less. So pairing energy will be higher than delta naught value. Okay. And what is the most stable state for square anti-prismatic geometry? So here the solution I think I have already explained. You can uh, see that particular video. Okay. So you can see the dz square orbital is stabilized here. Okay. So this is the most stable state. So apart from that, there are other geometries also. You can just remember their geometries and the splitting of the orbitals in these type of complexes, whether it is linear, trigonal, tetrahedral, square planar, trigonal, pyramidal, and square pyramidal or octahedral. Octahedral is easy, that is T to Z and easy. And if I remove these two bonds, it will become the square planar complex, this one. Okay, hence the repulsion on the z axis is very less, so that's why these three terms are stabilized and the energy is reduced. And you can see on the x-axis and y-axis there are very high repulsion, so that's why they exhibit the higher energy. Okay. Okay, so here are three tetrahedral complexes. You have to identify what will be the right order for their uh, energy values. So if you know the spectrochemical series, okay, you can just arrange them in their splitting energy order. And because metal is same, so you should be just focused on the ligand uh, s- stabilization values. Okay, so if I write down, it will be Br minus SCN minus Cl and then NCS. Okay, so C will be having highest energy, then A, then B, because B is very weak field ligand. Okay, and calculate the CFSE value of this complex, that is tetrahedral. It is D7. Okay, so it will be E, it will be T2. Okay, just fill them. Okay, so it will be zero point 0.6, it will be plus zero point 0.4, 3 multiplied by zero point 0.4 del T, and minus zero point 0.6 multiplied by 4. So it will be 1.2 del T minus 2.4 del T. So it will be minus 1.t del T, or you can say 12 dq. The many coordination complexes are colored due to Evaporation of solvent from the complex lattice, formation of solvent coordinated complex in solution, electronic transitions. Okay, electronic transition is the main cause for the coloration of coordination compounds. Okay, in the second one, in the total number of microstates for the term will be, just apply this formula, that is 2s plus 1, 2l plus 1. Okay, so this is the value of multiplicity, that is 3, and SPDF, it is 1, so it will be 3 multiplied by 3, that is 9. Okay, for a transition metal complex, if the metal center is highly reducing and ligand is highly oxidizing in nature, then type of charge transfer occurs. So highly reducing means, what does that mean? It should have a low oxidation state or high oxidation state. It is accepting the electrons or losing the electrons. And ligand is highly oxidizing in nature. That means it can easily accept. So metal to ligand charge transfer can take place here. Okay. The intense purple color of potassium permanganate, ligand to metal charge transfer transitions. The compound which show metal to ligand charge transfer. For MLCT, the complex should have a sigma donor pi acceptor ligand. Okay, so you can see CO is a sigma donor pi acceptor, so that's why it will show MLCT. Okay, okay, just I will pause here for 2 to 3 minutes. Thereafter, I will discuss the more questions. Okay, so today I have a very long lineup of questions. Okay, so increasing order of wavelength of absorption for the complex ion. Okay, so the wavelength is directly proportional to, you can say, frequency, or reversely proportional to lambda. So higher the energy difference, lambda will be lower. So in case of this, because it is a strong ligand, the energy gap will be higher and lambda will be low. Okay, so 4 is less than first, because after that it is a strong ligand as compared to this one, and then water, and then chloride. So since it will be creating very less energy gap, so lambda will be higher for this one. Okay, in octahedral crystal field, the free ion term D will be split to T to Z and EZ. Okay, the original diagram given below is applicable for D3 octahedral system. Here the answer is already written. So both D3, D8 octahedral complexes. Okay. Yeah. Among following the necessary requirements for transition metal complex to show MLCT transitions, metal should have a low oxidation state. Yeah. The ligand should have low lying empty molecular orbitals. The metal center is in high oxidation state. Okay, so this is wrong statement. The ligand should have low lying completely filled orbitals. Okay, so this will. I think these questions we have already discussed in detail. The ground state term for this one, that is titanium plus 3 D1. Okay, and here you can see the spectra. The ground state term will be 2T to Z. Just remember the original diagram and write down the when excited state or the ground state. Okay. According to Tanabe-Sugano diagram for D5 system given below, the number of spin allowed transitions possibly for, because it is a D5 systems and the weak field. So that's why this region we have to look for. So here you can see the ground state is having a multiplicity of 6, but in the excited states there is no state or no any other level that having a multiplicity of 6, so there will be no transition, especially spinal route. So none of them. Okay. The organ diagram gives information about weak field complexes, and Tanabe Sugano gives about the weak and strong both. Okay. Now moving forward to the spinals. How okay? So how you will identify the spinals, right? So if you are having the crystal field stabilization energy of a tri-positive ion in octahedral field is greater than all of the ions, it will be having normal spinel structure. And if the crystal field stabilization energy of A plus 2 in octahedral field is higher than others, it will exhibiting the inverse spinel structure. Okay. So the first one is the 4. This type of spinal structure, the iron plus 3 will occupy. So first you have to determine whether it is a normal spinal or inverse spinal. Okay. And thereafter you can easily tell that the plus 3 ions will be occupying which sides. Okay. So here is the explanation. Because it is a inverse spinal, so uh, one Fe plus 3 is in will be in octahedral side and other will be in the tetrahedral sides, because the fraction of plus 3 in this case will be zero point 0.5, that is lambda value. Okay. And what about this one, the correct spinal structure of CO3O4, because it is inverse spinal structure, as I have explained, the cobalt 3 will be occupying the tetrahedral as well as octahedral sides. Okay. So I am moving very fast because since these problems have been already discussed. Okay. So for this complex, there will be orbital contribution to magnetic moment from ground state, first excited state, neither in ground state nor excited, or both ground state and excited states. Okay. So just write down the electronic configuration and see whether T term is symmetric or unsymmetric, and you can get the basic idea from there. Okay. And in second one, in an octahedral metal complex with sigma bonding ligands, the set of orbitals that participate in sigma type bonding interactions. Okay. So in octahedral metal complex with sigma bonding ligands, there is no ligand group orbital of matching symmetry with the T2Z metal orbitals, because they involve in the pi bonding. Okay. So hence T2Z setup remains as non-bonding molecular orbitals. So if I talk about the octahedral metal complex formations, all the ligands come through on the axis, non in between the axis. So overlap is not there. So that's why they remains non-bonding. Okay. So what will be the correct set? T1U, EG, and A1G. Okay. Yeah. The next is in a octahedral complex, T1U bonding and antibonding molecular orbitals are obtained when this ligand group orbitals combined with. Since it is having a degeneracy of 3, okay, so it will be uh, overlapping with the metal orbitals which are having a degeneracy of 3 or having a same symmetry. Okay, so p orbitals are the matching orbital which have the same symmetry of Tu. Okay, so that's why they will overlap. Okay. The expected spin only magnetic moment for this complex, that is vanadium plus 4. Okay. So it will be D1, and you can just calculate Using this formula, it will be point under root 3 Bohr magnetron, that is 1.73. Okay, the complex with spin only magnetic moment 5.92. Basically, from this value, you can get the idea that which complex is having 5 unpaired electron. Okay, so if I talk about this one, that is Fe in plus 3, it will be 35. And since it is a weak field ligand, so the electron filling will be like this. And if you put the unpaired electron, it is under root 35, so it will be approximate 5.92. Okay, you can check for others also. Okay, for orbital contribution in magnetic moment, which is the incorrect statement? Orbital must be non-degenerate. No, they should be degenerate to each other for the contribution in magnetic moment. Yeah, this is the right answer. They should have same shape, because in orbital contributions, you can just talk about the same shape, and interchange of electrons between there is causing the magnetic moment basically. Okay, so among the following metal complex is the most labile one in terms of this exchange reaction? Okay, first one. Okay, so in these four options, you can easily observe they all are hexa-coordinated complexes, but this one is tetra-coordinated. Okay, so it will be most labile because it has enough space to accommodate the incoming ligand. Okay, moving to the next one, the rate of exchange of water present in the coordination sphere by this isotopic water molecule of this follows an order. So basically, you have to identify which one will be more labile to the uh, exchange rate of this isotopic water molecule. Okay, so if you know the answer, just tell me. Thereafter, I will explain. Since here I have discussed the content of week, I think week 9 and week 10 up to. Okay, so I have mostly discussed every concept for your revision. Okay, so if you want to determine the lability of any complex, so I should be familiar with the axial bond if it is elongating. Okay, so basically the rate of exchange depends upon few things. First is the size of cation. Second one is John Taylor distortion, and third is size to charge to size ratio. Okay, yeah, so in this case it is D9 configuration, and if I fill them, sorry, it is 2. So you can see the easy, the electron configuration, let me write easy 3. Okay, so easy is unsymmetric here, so John Taylor distortion will occur. So that's why this complex is more labile among the all. And if I talk about the other one, in second is manganese plus 2, Fe plus 2, and nickel plus 2. If I talk about their sizes, so it is having great size and it follows its this order. Okay, so what will be the right answer? So first is highest among these, then second, then third, then fourth, because less will be the radius, less will be the lability of that complex. The last, but the not least, the slides. Among the following, the correct statements about associative ligand substitution reaction are: In associative ligand substitution reaction, intermediates have higher coordination number. Yes, that is right. And complex with lower coordination number undergoes associative ligand substitution reaction more rapidly. Yes, because it can accommodate the incoming ligand. So in that scenario, the associative ligand substitution reaction take place. And rate of associative ligand substitution reaction depends upon leaving group. No, it basically depends upon the incoming group. Okay, because let's say if you are having any complex, right? So if the bond between this metal and this incoming ligand is strong enough as compared to these bonds, so it easily replace them. In the case of dissociative mechanism, in the case of dissociative mechanism, it the bond strength will be less and it will be going outside, and incoming ligand will be easily occupy this space. Okay, so A and B will be the right answer. Direct electron transfer between two metal centers occurs in the case of outer sphere mechanism, inner sphere mechanism, both outer sphere. Because in you know uh, in inner sphere mechanism you need a bridging ligand like halides. Okay, and in outer sphere mechanism there can be direct electron transfer. Okay, so there is no intermediate formation as it is in the case of inner sphere mechanism, which basically should contain the bridging ligand. Okay, so for your information you have to remember this trans series, so that you can get the idea about the reactions that is taking place with the square planar complexes. Because if you remember this trans series, you will be able to attempt uh, the reactions very successfully and get the right product. Okay, because as will the trans effect series will greatly help you in deciding the stereochemistry. Because because the trans ligands of these complexes is highly that bond is highly labile and it can break down, and the incoming ligand is attached there. Okay, so that is the significance of this trans series. Okay, so thank you for the attending this revision session. Mostly I have discussed all the concepts of 12 weeks, right? So if still you have any problem, you can post your questions in discussion forum. I will get there and will respond. Okay, so thank you for attending this session. Have a good day. Okay, so okay, you want to ask something, Purnima? Yeah, thank you for attending. You can see the recording of this session. Okay, okay, yeah, thanks for attending.